So we said in the previous parts, there is so many methods how we can estimate the growth of the function, and that growth of the function, we use it to estimate how bad the algorithm or a program could go all the way to infinity when the input size is really, really large. And just to give you a sense of this, consider this scenario where we have insertion sort, merge sort, and a quick sort, and we want to compare between them. Now, the first scenario we take is when we have a home computer, and the second scenario when we have a super computer. Now, insertion sort in a home computer will be instant if the input size is 1000. Now, go to billions of input, you will find that insertion sort in a home computer takes 317 years to finish, and 1 week in a supercomputer, which is a very, very long time. So imagine you go to Google and search, for example, the definition of proposition or logics or matrix multiplication, and you have to wait 1 week for Google to get back to you with the best result. The same scenario with merge sort. And now remember, in insertion sort we say the time complexity is n to the power 2. Now merge sort is a more advanced sorting algorithm, and we reduce the time complexity from n to the power 2 to n log n. And look how much gain we got in the time and the execution time of the algorithm. So when you have 1 million input, it will take a home computer 1 second. And if you take a supercomputer, you will have an instant result in that sense. So if you take billion input, a home computer will take 18 minutes to finish. Now, quicksort is like the flagship of sorting, and it has been implemented in many products and many environments. You will find, because the time complexity of a quicksort is n log n, it will take a quicksort 12 minutes to finish sorting 1 billion input, and a supercomputer will basically take an instant result. So the first lesson we can get from that the growth of the function is very important for us as a computer scientist, because we can use it to estimate how bad a computer program could behave. And we can learn that this is better than having a supercomputer, and a great algorithm are better than good ones. Now let me tell you the easiest guide to find and to estimate the time complexity for any algorithm. So when you look to any program that computes, for example, the running time of the sum of 5,500, 10,000, and 1,000 element. We run the program with a data set of varying size, and we say if we have an array of different size, and another assumption we have basically is that it is already sorted. Now we want to compare the running time and the result for all these given set of data, and we can plot the result. X-axis, the input size, y-axis is basically the result of the time. Now what you will notice, the running time is always proportional to the input size, regardless of any hardware or software environment you take, and this means we can take the first approach. That if we implement a programming language, an algorithm in a programming language, and we run the program, and then we basically measure the performance, and we use a stopwatch to measure the result, and we compare when the input size is 5,000, when the input size is 10,000, and when the input size is 1 million. The second approach is to use the big O notation, or the growth of the function, to estimate the execution time of any program or any algorithm. Now we will find that the stopwatch approach, which is the experimental study, is not useful in computer science for many reasons. Not every single algorithm we have is already implemented. Also, we have no time and freedom to wait for the software engineer to finish the coding and then we estimate. We want to give a rough estimation before you go to the implementation phase of the algorithm. So we will take now a generic methodology to analyze and to estimate the time complexity Now let me go in a specific. When you have a higher level programming language like Python and C, and we say which is faster, x less than 10 or x less than or equal 9. Those two statements, regardless which programming language, they will take the same time unit. So regardless how many seconds we take, it is basically the same time for us. So we focus every time on the loop, not on a specific operation. So we speak on any repetitive routine and procedure, not on that specific arithmetic operation or arithmetic assignment. Now we take a constant, let's say k, and this k is such that the operation always take k nanoseconds. So we can assume that any operation could take k of nanosecond. Let's say, for example, x equal 2, it will take 1 nanosecond. Print Python, this will take a nanosecond. So any program which have only one simple statement or one simple operation will take that k, a constant of nanosecond. So regardless how much the input size is big or small, that program will behave the same. It's 1 nanosecond and there is nothing more than that. But when you have a program which is a linear time, in a sense that it has in it a loop, then when you go for I equals 0 and I less than n and I plus plus. Now assume that statement j equal j multiplied by I, it takes k of nanoseconds. This means we can multiply k n times, so this is k multiplied by n. So that loop will take k nanosecond multiplied by n. Let's say that k is 2 nanoseconds. And we have the input size 100, so this means 2 multiplied by 100 equals to 200 nanoseconds. So this loop will take 200 nanoseconds to finish, which is not too bad. Now take n, the input size, to be 1 billion. I multiply 2 nanoseconds with 1 billion, you have 2 billion of nanoseconds, which is a large time to wait for. If we have two algorithms to solve a specific task, let's say algorithm A take 500 time unit to finish, and the second one is basically take 100 multiplied by n times unit to finish. Now which is better? If you look now, algorithm B is better if our problem size is smaller, when n less than or equal 50. Because every time we go more than 50, this means we have to have 100 multiplied by 50, which is 50,000. So they will be in the same time. Now let's take n equals to 100. 100 by 100, this 10,000 unit of time to finish in problem B, and this means we have now a bad algorithm. But how we can know that? We will start now to give you an ultimate guide to use and to apply to estimate any time complexity of any problem. I wish by now you understand what's the problem. Now let me show you what is the solution for that. Again, so big O notation is basically a simplifying and estimation of the running time of any algorithm. You can take, if an algorithm takes C multiplied by n to the power 2 plus D multiply n plus E time, we simplify this formula and we say, and we take the largest term of that equation and we say that algorithm could go all the way to big O of n to the power 2, because this is the worst case scenario for this equation to go. And we can verify this if we just assume that n equal x and we basically simplify all the equation, we will get n to the power 2. And this is what we call the big O notation. As example of this, take for example 7 multiplied by n minus 2. This algorithm could be described in different way, but normally it will behave all the way to big O of n. It will never reach big O of n to the power 2. But if you take the second one, 3 multiply n to the power 3 plus 20 multiply to the n to the power 2 plus 5. Every time you see this, guys, simple steps. First, ignore all the constants. Throw all the lower terms in the C and keep the larger term like n to the power 3. So the second equation is big O of n to the power 3. Let's say you have another equation which is basically saying the time complexity algorithm is big O n to the power 4 plus big O, the time complexity of the algorithm is n to the power 4 multiply 5 plus 3 multiply n to the power 3. Remove the 5, remove the 3 as a constant, ignore n to the power 3 and take the largest guy in the equation, which is n to the power 4, and just simply say the big O is n to the power 4. And this is the easiest way to estimate the big notation, because we are describing the growth of the function. Now you might be saying, how on earth I will ignore the constant on all these simplest terms? Take this example when r of x equal x to the power 2 plus 3x plus 5. Take x equal 1 and see the time. Then take x equal 10, then see the time. Then take x equal 100 and see the time. And then take x equal 1000 and see the time. You will find that 5 all the way it will remain regardless how much the input size is. Then when a 3x, that 3x is growing very slowly comparing to x to the power 2. You will find that our function will grow when x to the power 2 increases the input size. The summary of that: a constant big O is a very, very good and optimal. And we have only one algorithm to do that, which is basically including a sequence of a statement with no loop. Now, the better is log n. The good is big O n. The acceptable level is n log n. But when you look to the code, how we can find those things? Let's take scenario by. The first scenario is when we have a sequence of a statement. Let's say we have a statement 1, then statement 2, all the way to statement k. This is a sequential program, no loop, no exception in it. Normally, we just do the time of statement 1, which is that k nanosecond, plus the time of statement 2, all the way to statement k, which is basically a constant. Once the execution time is a constant, we roughly say this is big O of 1, because there is no growth of any function in this example. Why there is no growth? Because everything we go after we execute each statement, we will end up with a constant. Now what if we have if-else statement? Every time you see if, then else statement, you take the maximum of each block. So if we have if condition, then block 1, else block 2, we take the maximum of each one. So we will focus our attention to one simple block rather than 2. If we have a loop, execute n times, then we take that n, the input size, multiply by a time unit, and we can roughly say that it is normally one simple loop is big O of n. If we have nested loop, then we need to do multiplication. We take the time complexity of the outer loop and we say it goes from 1 to n. Then this inner loop is going from 1 to n and we multiply n by m and we end up by n to the power 2 if and only if the m in the inner loop also goes all the way to n, not n divided by 2 or log n, because sometimes you have to pay attention to the inner loop to see that this loop is behaving as a sequential search, maybe insertion sort, maybe bubble sort. So in this case, if the inner loop is a bubble sort, it will be n multiply n to the power 2 and the result will be n to the power 3. Now every time you see a statement with a method call, a function call, you have to ignore that call function and you go and you inspect the function itself. So inside that function, if you find one simple loop, this is big O of n. 2 nested loop, this is big O of n to the power 2. 3 nested loop is going to be n to the power 3. Maybe in that function you do binary search, which means you have log n time complexity. Okay, so let us take now an example. In this example, we have a loop, and that loop, outside it, we have another loop. And we say when we have those statements, we calculate the time complexity for the first one, which is big O of n, because it goes from I equals 0 all the way to n. Now, the second loop is also going from j equals 0 to m, so this is n plus m. And we say the generic rule is to ignore constant, and we take the higher term. And in this case, it will be 2n, and we ignore the constant 2, and it will be big O of n. Now, in the second example, we can see there is two nested loops, and there is one loop outside those two nested loops. In this case, the first loop is going all the way to n, and the second loop is going all the way to n, so this is n multiplied by n, so n to the power 2, plus n. We ignore the lower term, and we keep the bigger term on the equation, so this basically big O of big O of n to the power 2. Now, every time you see a linear algorithm or a loop is behaving in a linear way, in a sense that the increment of the loop, as you can see here in the example, I is going to 1, I less than or equal to n. Now notice that I, how it is incremented. I equal I plus a constant. Maybe it's I plus I equals I plus 1, or I equals I plus 2. So every time you see an addition or minus in the increment of the loop, this is a linear function, and that loop straight away is big O of n. But sometimes you see that the increment is basically a multiplication or a division. In this case, once you see the counter of the loop is going all the way to I equal I multiply a constant, or I equal I divided by a constant, then the time complexity for this loop is log n, because it is a divide and conquer loop. Now, the third example, when we have a loop and the increment of that loop, I, is going all the way I equal I to the power constant c, or it is I to the power 1 over a constant c, then in this case the time complexity is going to be the log of log n, and this is basically another type of an algorithm where we have the time complexity log n, and it will be 2 to the power n, which is a very expensive algorithm to have. So as an example, we have here two loops are nested, and you notice now the time, the increment is basically plus in both loops, so those are linear. So these are n multiplied by n, so this is n to the power 2. Finally, let us take more examples. You will see in the first example, we have a loop going from k equal n, and k greater than or 0, and k is minus minus. Based on our guidelines, we say when we have in the increment minus or plus, this big O of n. Now, the second example, we have two nested loops. Now, the first one is going I multiply 2, so there is a multiplication or a division, so this is basically a log n. Now, the second loop is going from j equals 0 to j less than or equal 1, so this is basically log n, because in this case, in this specific scenario, j is not going all the way to n. It will never reach the value of n at any case. Now, if you want j to reach the n value in the nested loop, look to this example. Here we have the first one with multiplication, so this is a logarithm, not a linear function. So the time complexity for the outer loop is log n, and the inner loop is going from j equals 0 all the way to n. Now please notice that the less than or equal sign in the inner loop is different from the previous example. In this case, in this program, the time complexity is n log n.